And we have our third and last problem here. OohMoo Milk? OohMoo Milk? All right. Um, so for this problem, we have like Farmer John with a bunch of bottles of milk, and then every day he's gonna fill 8 of these bottles with 1 extra unit. And every single day, Farmer Nahaj, our favorite op, is going to take 1 unit of milk from B of those bottles. And the idea here is they're both going to try to play optimally, and we want to figure out what's the maximum amount of profit Farmer John can have at the very end, no matter how Farmer Nahaj is. Okay. And also, the profit for every single bottle is m squared. Okay, so let's get into this one. So the first thing we can note is there's no harm in sorting the bottles, right? So let's just go ahead and sort our bottles for this sample input. So we have 10, another 10, another 10, another 8, and 4. And based on this idea of being able to sell everything for m squared moonies, it should be apparent that we basically want to increase. So let's take Farmer Nahaj out of the picture for now. We basically just want to increase the bottles that already have a lot of milk, because as you increase things that are bigger, you get more out of the m squared, right? As we're far too aware with n squared algorithms. Okay, so Farmer John's strategy is very simple. Every single day, he's just going to take the most filled milk, or like full bottles of milk, and fill them up more. Right. So in this case, A is 4. So each day we'll just bump these up by 1. Okay. Now it turns out Farmer Nahaj's strategies is just as simple, right? Basically, Farmer Nahaj will every single day look at all the bottles of milk and go ahead and just decrement the B bottles of milk that are the greatest. So let's just start with a quick simulation on our sample here, very naively. So first, we're going to bump this up to 11, 11, 11, and 9. And then Farmer Nahaj is going to decrease this one to 10 and decrease this one to 10. And these stay the same. Cool. So after one iteration, we have this much milk in all of our bottles. Now, after a second iteration, right, Farmer John's going to end up increasing the same stuff. So this will become 11, 11, 12, 10. Okay, great. And Farmer Nahaj will, let's say, decrement this one to 11 and decrement this one to 10. Also, it doesn't matter if he decrements this one to 10 instead. Cool. So after 2 rounds, we'll be at this array. And we can just keep going. So again, Farmer John just looks at the top 4, increments them, and so on and so forth, right? Yeah, now Farmer Nahaj has to decrement these 2. Okay, and yeah, just keep going. And at the end, you can just print out your array, or each element of your array squared, and the sum of that. Okay, so this would be a, let's see. So for every single day, it's a O of A plus B runtime, with maybe a log factor to find the largest one you can, or the largest one to increment or decrement. So yeah, if you just naively implement the simulation like we discussed right here, then it'd be D times A plus B times log N. Right. So now all this is fine. It's just this factor of D is too large because D is huge. Okay. Cool. So now let's go ahead and think about how we can optimize this. Well, the first thing to note is Farmer John is always increasing more bottles than Farmer Nahaj is decreasing. So like we know Farmer John is kind of like net making, and no bottle of milk is going to start lower than or end lower than it originally was. So let's think about some cases here. So first of all, we have these 4 bottles of milk getting incremented initially. We have these 2 bottles of milk getting decremented. And we have this bottle of milk, which is not getting changed at all. So the first thing to know is this bottle of milk that's not getting changed on round 1 is never going to get changed because we're increasing the top A, and then Farmer Nahaj is going to decrease the top B. So there's no effect on this. And everything within the top A is at least going to stay the same, right? So if you're not in the top A initially, you're never in the top A, and therefore we can just output all of this part, or just calculate the answer for all of this part without worrying about it at all. Okay, so now let's just consider a smaller array. Now our array is of length A. And this array of length A is getting incremented once, or is getting incremented every single round. So we actually don't need to increment every single round anymore. Why don't we know this is our fixed length array, and every round, for all D rounds, we're going to increment them by 1. So let's just go ahead and replace all of these values with D plus their original value. Okay, great. So let's do that. So this becomes 14, 14, 14, 12. And then again, we don't need to worry about this for now. Cool. So now the question is, how much can Farmer Nahaj decrement these to minimize Farmer John's ending value? Right? And this is a little bit tricky because you want to make sure. So first of all, we can calculate that Farmer Nahaj is going to decrement a total of 8 units, right? Because we have like 4 days in this example, and Farmer Nahaj decrements 2 every single day. But you're not allowed to decrement any of the bottles below their starting point. So for example, this 14, you can turn it back. You can turn to like a 13, you can turn to 12, you can turn to 11 and 10. But if you try to turn to 9, that's not allowed. And the reason is because you can only decrement by D because every single day you can only decrement by 1. Right. So we need to somehow figure out how we can like do the decrements quickly. And without exceeding the total. So basically our constraints are, here's the number of decrements you have to do total. We want to ideally, like naively, we want to decrement the largest ones every single round. And we need to make sure no one drops below their original value. And as an example of why you might ever want to do that, so let's say this number started out as like 100. Then after the update, this gets changed to 104. If Farmer Nahaj would ideally want to decrement all 8 from here to minimize Farmer John's value, but he's not allowed to because he only has 4 days to do the decrements. Right? And this is like the slightly tricky part for the simulation. Okay, so let's go through how we can do this. All right, so essentially the idea is we're just going to try to move each of our buckets into the bucket here being the set of milk bottles with the same maximum amount. Because if you like naively simulate this, one way to think about it is, all right, let's go ahead and decrement the largest bottle. Let's go ahead and decrement the largest bottle again. And so every single iteration, you just pick the largest bottle to decrement. And once the largest bottle gets decremented to their original state, you can no longer pick them. Right? So naively, I can change this to like 103, and then 102, and then 101, and then 100. Great. And we've done all these decrements, and I can't pick the largest bottle anymore because it's been decremented to its original value. So now I have to decrement this 14 instead to 13. And then next I would decrement this to 13, then this to 12, then this to 12. And then we run out of operations. But if we had more operations, then we could keep decrementing any of these 12s down to 11. Right. So that's like essentially the simulation process we want to speed up. So let's go ahead and try to do this in bulk. So the first thing we can do is let's go ahead and look at all the bottles with the maximum number. And then we can go ahead and decrement all of them down to the next level, but it also depends on if they already end up at their same level. So let's go through one of our cases here. So one possible test case is something like this, right? Where we're trying to decrement all the 104s down to 14. But we notice like, oh, you can't actually go all the way down to 14 because the original number is 100. So then in this case, you can only decrement your 104s down to 100, or your 104 down to 100, and then you have to start fresh from here. Let's go through another case where let's suppose you have like a 12 here. Okay. And this becomes 16. All right. And again, we're going to try to do a total of 8 decrements. So what we're going to do here instead is we are going to start by decrementing this down to 14. And this is like a O of 1 operation so far, because we just look at how many 16s we have, one of them. We decrement all of them down to 14s, which takes a total of 2 operations, right? So this gets decremented to 14, and this gets changed to 6. And this was O of 1. We're not simulating like turn by turn, right? Okay, now we have 3 14s, and we're trying to decrement all of them down to 12, right? Okay, so we're going to try to decrement them down to 12, and now the number of operations needed is, let's do a slightly different example, sorry. Make this a 7, and make this a 11. Okay, cool. So now we're going to try to decrement all 3 of our 14s down to 11s. Now we can just do the math where it would take 9 decrements, but we only have 6 decrements left. So therefore, we would actually stop the algorithm right here and evenly distribute all of our decrements, right? So in this case, each of them get 2 decrements, and that's it. And we have like 11, 11, 11, or sorry, 12, 12, 12, 11. Okay, so let's say we have like 7 decrements instead. Then this is another case where it's like if it doesn't evenly divide, then at the end you're going to get something like 12, 12, 12. This is evenly splitting the 6, right? And then you have one more, and you can just apply it to any of them. So exactly one of these 12s become an 11. And then this would be your final array that you just take the squared sum over. Okay, now the hardest and yeah, the trickiest case is how do we know? Because basically we're just tracking for a given, like at any point, we basically track what is the most full bottle of milk and how many bottles are that full, right? So in this case, all we know is the most full a bottle is 14, and 3 of them have a fullness of 14. And then, yeah, so now the question is, suppose we have like a lot more decrements. So suppose we still have like 20 decrements to go for some reason, right? Then how do we know that like we cannot actually change all of these down to 11, right? So if we have like 3 14s here, but this first 14 actually originally came from a 16, which means this value, the lowest it can go is only 12, whereas these can go down to 10, right? So now if we calculate the number of operations we need to get down to 11, we'll be like, okay, we just need 9 operations, so we change this to 11, and then we now have like 4 11s. But that'd be wrong because this can only go down to 12, right? So instead, what we can do is we can essentially compute a separate array. So instead of always going down to the next like available units of milk, you can try to go down to one of these original values as well. And the reason why we need to take a pause at the original values is because when you get down to the original value, you can no longer decrement certain bottles. So the example here is if we had 116, then once you decrement these 3 14s down to 12s, you now only have 2 bottles of 12 that you can continue decrementing, right? So basically for each of your original values, you need to take a pause at those positions as well. And also you need to calculate for each of these positions, how many bottles you'll lose. So basically once you decrement your top bottles down to 12, you lose one of your top bottles because you can't decrement any further on that one. And similarly, if you decrement all of your top bottles down to 10, you lose 2 of your top bottles to decrement further because they're not allowed to go past 10, right? Yeah, and that about sums up the whole entire algorithm. So just to kind of summarize, our main observation is that you can sort all your bottles of milk, and you only need to take a look at the top A bottles and also the top B bottles, right? The other bottles can just directly be summed into your answer and forgotten about. Now, within your top A bottles, you're going to increment all of them every single turn. So you can just go ahead and add D to all these values. And then now the decrement process is the tricky one, right? So we can calculate the initial number of decrements we're going to do. And this is just B times D. So we know the total number of decrements we can do, and we also know the maximum amount we can decrement each value by. And then for our simulation process, we just track a few things. One is how many top bottles there are. And the other thing is what is the value of the top, like the top bottle, right? Value being how full are they? Okay. So number of most full and the actual like fullness, just say that. And then essentially we're just going to try to decrement all of these, like batch decrement them together down to the next fullness. And the next fullness depends on one of two things. So it's either one of the original fullnesses, or it can be one of the new fullnesses after we've added D to everything. So you can essentially just construct a new array with all of these values and sort them. And you always decrement down to the next smaller one. And then for each of these original fullnesses, you know that once you get to here, you lose some of your top bottles. So the example here being, suppose you have like 16, 14, 14. So if you decrement all three of these bottles down to 12, only two of them can be decremented past 12. So at this 12 we lose one of the bottles that can be decremented. And at the 10, we would record that we lose two bottles that can be decremented past 10, and so on and so forth. And then for these new values, although we also want to try decrementing to that amount, you don't need to record like how many bottles you lose, because every time you get to 16, 14, or 11 or whatever, you don't actually lose any bottles. Like you can still decrement all of them is the point. And that's basically the whole algorithm with a few like edge cases to like work through. Yeah. And if we think about our overall runtime, we have O of n to compute our initial array, and then to simulate, or O of n log n to initially like sort and add D and like combine the two arrays and sort again. And then we're going to go through our decrement process and kind of like batch decrement. So this part can actually be done in O of n, like because basically you're just processing. There's only two n elements to process, and for each element you can process it in O of 1 with some like if statements. So overall runtime is just n log n. Are there any questions on problem 3? If not, then that's it for our gold live solution for the US Open contest. All right. See you everyone.